Hi folks, this is Maria, and we're going to talk about radioactivity and nuclear decay. First, we're going to talk a little bit about what we learned in the in-class activity. I'll talk a little more about what nuclear decay actually is, connect it back to radioactivity, and then give you a question to just think about, write a few thoughts down, and come prepared for discussion in the next class. So one of the things you learned was that radioactivity is when an element has an unstable nucleus, and it's got to emit a particle and or energy until it does actually become stable. We definitely talked about that first part a lot. Maybe that second part wasn't quite as clear, but that's why we're talking about it now. What makes an isotope radioactive? So you actually saw the graph on the left-hand side of the screen in a slightly more complex form. And right now I'm just going to show it to you in this really simplified version. So number of neutrons is on the y-axis, number of protons on the x. The blue line is where the number of neutrons equals the number of protons. And then the line of stability, that just means it's where stable isotopes are found, aka not radioactive isotopes. Now, one of the things we talked about during class is that stability is linked to the number of neutrons. And it turns out that the more protons an atom has, the greater the amount of neutrons are actually needed to provide stability due to the increase in proton-proton repulsion. So what I mean by that is that if you have positive charges and you have a lot of them, you know that if you put a positive charge next to a positive charge, they're going to essentially try and go in the opposite directions. Well, if you have a lot of protons, then that becomes an even bigger problem. So that's why above a certain size, the nucleus just is actually too big for the strong nuclear force to hold the nucleus together. All right, so that's reviewing, refreshing what was from the in-class activity. Now I want to talk a little bit about what nuclear decay actually is. So what nuclear decay actually is it's sort of it's what the loss of the particle or energy is from the radioactive isotope. There's a lot of different forms, as you can see on the left-hand side, which you do not have to memorize that at all. Please know that. But there's a lot of different types that are out there. Turns out that not all radioactive isotopes actually do the same type of nuclear decay, but all radioactive elements do some type of decay. The result of nuclear decay will eventually be a stable isotope. As you can see here, there's a bunch of different things that can actually happen in the process. And it turns out that different types of isotopes do different types of decay. And the ones that you'll most frequently hear about when talking about nuclear decay are alpha decay, beta decay, and then gamma decay. And gamma is actually the one that when we're saying loss of a particle or energy, gamma decay is actually release gamma rays. And so that's energy that's being released. Versus if we're looking at alpha, it's this alpha particle, and then beta, we're looking at this. So these are all the different things that can happen. Now, one thing that's really interesting that frequently, or that can be a frequent occurrence, is that with nuclear decay, there can often be a chain reaction. And what I mean by that is that it'll release one particle, but it turns out the particle that it released didn't actually solve the whole problem. It's still an unstable nucleus, and because it's an unstable nucleus, it's going to release another particle. So there's things like what you see on the left, where we're starting with this isotope of uranium, uranium-236. You'll actually see this same sort of thing happen where it's a chain reaction, and this sort of thing will split into this, which will bump into this, which will generate another of this. These frequently are uncontrollable. There are some ways of controlling chain reactions, but the main thing that I want you to know from these is that these chain reactions actually release a lot of energy. Okay, and then if we're talking about how we actually detect radiation, we use something called a Geiger counter. And Geiger counters actually work by detecting either the particles or the energy given off during nuclear decay, rather than the radioactive isotopes themselves. So if you have this out and you're trying to figure out, okay, is uranium-236 around, you'll be able to detect the radiation coming from it, but you wouldn't necessarily be able to detect the specific isotope. So I wouldn't be able to detect, oh, this is for sure uranium-236. It's more, oh, this is this sort of decay that's happening, and therefore I'm able to detect that there is radiation actually going on. So when we say the word radiation, we're actually more talking about the particles that are being generated by nuclear decay. Okay, well, so thinking about all of that, and I've given you a decent amount to think of in just 6 minutes, I want you to go ahead and write down some thoughts for our next class discussion. So you've probably heard the phrase radioactive waste. You probably have the idea and the knowledge that nuclear accidents can have really, really long-lasting consequences for human lives. But there's also everyday uses of radioactive isotopes. So there's radioactive isotopes that are used for things like medical imaging. One of those radioactive isotopes can be really dangerous and harmful, and another radioactive isotope can be thought of as actually literally you ingest it as part of the medical imaging. And so I want you to just think about why that might be true. Why is one considered sort of safe to be around and one is considered extremely dangerous? Write down some thoughts, some ideas. You're not expected to come in with any sort of correct answer. And we'll come back to that. If you're wondering where I got the images from, these are the websites where I got the images from. And we'll see you next class.